Okay, for the assignment, you asked us to do web assignment 1, question 9 or 10. I chose number 10. And basically, the question asks or states that a man drops a rock into a well. For part A, the man hears the sound of the splash 2.53 seconds after he releases the rock from rest. The speed of sound in air at the ambient temperature is 336 meters per second. How far below the top of the well is the surface of the water? For part B, it's asking to find out if the travel time for the sound is ignored, what percentage error is introduced when depth of the well is calculated? Here I drew a picture showing that the speed of sound is 300. All right, I'm not on the laser pointer. Hold on. That speed of sound here is 336 meters per second. Here's the man dropping the rock. This shows that the time to go for the rock to fall and the speed of sound to come back up to hit the man is 2.3 seconds or 2.53. Sorry, it should be 2.53 on the one I did. 2.53 seconds. And here it's delta x to show the displacement, which is unknown. And it should be delta y, but it's okay. It's okay. Please don't mark points off. All right, here we have, I decided to use kinematic of delta x equals initial velocity times time plus acceleration times time squared. And, or it should be 1/2. What the? This was all right. It was just like there's a picture that I accidentally cut out and then it cut everything out. So 1/2 times acceleration times time squared. Here we know that the initial velocity is 0 meters per second because in part A, he releases the rock. He does not throw the rock downwards. He releases it. So initial velocity is 0 meters per second. So we can show that, multiply that by 0 to get the equation. Initial displacement equals 1/2 times acceleration times time squared. And knowing the acceleration of gravity due to gravity is 9.8 meters per second squared times 1/2 times time squared. And here we can divide 9.8 by 2 to get 4.9 meters per second squared times time squared, which equals displacement. And here I just rewrote it to get time alone. And so I have displacement over 4.9 meters per second squared equals time squared. And here I square root it. So I got the equation time equals the square root of displacement over 2.21 meters per second squared. All right. And then so this is to find time 1. And up here we can see I'm going to find what time 2 is, which is what the speed of sound that it's asking for. So here we can use the constant velocity to find that delta x equals velocity times time. Displacement equals velocity times time. So here we know that displacement equals the velocity, which is 336 meters per second, times time, which is the time upwards, which we're going to find out. Here I rewrote it to show that the time upwards equals displacement over 336 meters per second. And here we know that since in part A asks us for 2.53 seconds, we know that time 1 plus time 2 must equal 2.53 seconds, which is the time it took for the man to hear the rock hit the bottom. So here we decided to plug in time 1 or time 2 here, and then time 1 here, and set it equal to 2.53 seconds. I simplified the equation a little bit by multiplying both sides by 336 meters per second to get delta x plus 151.79 seconds times the square root of delta x equals 850.08 seconds. Now I subtracted 151.79 seconds times square root of delta x onto the other side and 850.08 seconds to the other. And then so I can square it. I don't know why it didn't show up here. Here, I'll do it really quick. But hold on. Here it should be 23040.2 times delta x. Yeah. No. Why? What? All right, I think I could just get rid of this line right here. Don't worry about that. All right, here we will square both sides to get this equation down here. And what is this? Why is it recording? Hold on. I don't like this notability up there, I'm not gonna lie. All right, so I expanded this equation on the left to get this equation here. And I squared this to get 23040 times delta x, which got rid of the square root. And then I combined like terms to get the equation of delta x squared minus 24,740.16 seconds times displacement plus 722,636.01 seconds equal to 0. I use the quadratic, negative b plus or minus square root of b squared minus 4ac all over 2a. And you can see I plug them in here. And then I simplified the radical out to get this of delta x equals that, plus or minus that, all over 2. And so what I did was I solved for both. So one possibility is this one right here, which was when I added these two together divided by 2, which is 24,710.92 meters. The second option when I subtracted these was 29.244 meters. And you'll see later on that this is the one you'll want to use. So what we're going to do is now test to see what is the most reasonable time off of these distances, this displacement. So here I brought this number back here, 24,710.92 meters, back to the time 1 equation, and I plugged it in for delta x. Here I plugged it in, simplified it down, and I got the time of 71.13 seconds, which is too big for what we're looking for, which is 2.53 seconds. So we know that this one is not going to work, so we can already cross this one out. And we're left with this one of 29.244 meters. And so we plug this one in, and we simplify it down. We plug it back into the time 1. We simplify it down. And just to know that time 1 is the time downwards, and time 2 is the speed of sound back up. So we plug it back in, simplify it down to get 2.45 seconds, which, in my opinion, is good enough. And because we're still yet to find the time back upwards. So I know that this one up here will not work, so I don't even bother plugging it into the time 2 equation. So I use this delta x with 29.244 meters, and I plug it in here into the time 2 equation, which we got back up here. And I simplify it down to get the time of 0.087 seconds, which also good enough. And so remembering that time 1 plus time 2 equals 2.53 seconds, we added these two, 2.45 seconds plus 0.087 seconds to get the time of 2.53 seconds, which is correct in the time that it asked for up here, 2.53 seconds. Now, that's part A. So we know that part A, it's asking for how far below the top of the well is the surface of the water. And we know by process of elimination, it is 29.244 meters from the top of the cliff. Now, for part B, it's a little easier. Basically, all we're going to do is completely neglect and forget about time 2. And we're going to set time 1 equal to the total time, which is 2.53 seconds. So I go back to the time 1 equation, and I plug in 2.53 seconds for time 1. I multiply both sides by 2.21 meters per second squared, 5.5913 meters. Square both sides to get rid of the radical. I get 31.263 meters, which equals delta x. Now, I need to use the percent error equation, which is experimental minus experimental minus calculated absolute value all over calculated times 100 to get the number 6.9% error. And yeah, that's it. Connor Grafin is in a call with me, and he says, "Hi, Mr. Lesher." He says, "So does James Kitchen." All right. That's it. Bye. Don't take points off, please. I know I messed up places, but